All right, so in this video, we're going to look at exponential functions, the graphs of them. And more particularly, we're going to be given a graph, right? If we're given a graph, we want to make the function that would make this graph, right? So we're going to kind of go backwards here. Now, before we look at these, I want to review some of the characteristics of an exponential function, because I'm going to try to do this in a very particular way that we can do this systematically and kind of approach every problem in the same way, because exponential functions can be a little tricky to make the function from the graph. So I just want to take some time to do this first. So if you remember, the basic setup or the basic kind of way to look at an exponential function is a times b to the x, right, where b is the base to the exponent and a is a multiple to it. So in terms of the graph, a is going to be the initial value, as I like to call it, right? In terms of x being 0, right? Anything raised to 0 is 1, so it's our initial value. And then if you watched these with me before, I'll go to the right one, so I'll say this is my a times b value, and to the left one, this is a times 1 over b. So if I go to the left, it's a times 1 over b. If I go to the right one, it's a times b. So in this case, a is 1 because there's no multiple. So the initial value is 1, which we can see from the graph. If I go to the right one, it's going to be 1 times 2 because a is 1, which is 2. And if I go to the left, a times 1 over 2 is a half. So we can see that it pans out right there. Okay, so just recapping those three main points. So let's start to move along here. Okay, so let's look at these two. Right, again, I need to keep on the review of some of these. So if you think about how this works in terms of what we just did, right, a is 4 here is the initial point, so it's going to start at 4. And if I go 1 to the right, a times b, 2 times 4 is 8, so we can see that. If I go to the left, 4 times 1 over 2 is half. Half of 4 is 2, right? So we can see the graph here. But in this case, this would be taking this shape 2 to the x, which is which one we just graphed up here. And then since I have a value added to it, that's a horizontal shift left 2. So if I took my main points, right, if we look back at this one, if I took my main points, the initial point at 1, because a is 1 here, and if I took my initial point 1 and moved it left 2, right, then I'd be placing it on the graph. When I went right 1, we said 1 times 2 is 2. So here, again, if I move it left 2, we got on the graph. If I went to the left, 1 times a half is a half. And then if we move it to the left 2, we can see that it matches up, right? But let's say we look at it, it still has an asymptote at 0, right? The initial point here, in terms of the y, if I let x be 0, the initial point we could say is 4, right? And then if I come 1 to the right, you can see that the value 1 to the right is 8. And if I go 1 to the left, the value is 2, which is the same thing as this graph. So if I have an a value, then this essentially turns it from a horizontal shift, right? If I wanted to do properties of exponents, we could say that this is 2x times 2 squared, right? Because if I have common bases that are being multiplied, I could add the exponents together, right? So I could turn 2 squared into 4, and then it would be multiplied by 2 to the x. So these two graphs are identical. We're just approaching them in a different way. Now, it becomes a little difficult to think about where the initial point is, because the initial point could essentially be anywhere. But if the initial point is 1, then this creates a very common process, and this is kind of the approach that I'm going to take. Now, before we do that, I want to say, well, what if we have something like this, right? So in a case like this, we can consider it the same way. Instead of graphing these, I'll kind of look at this one and show how these two are the same. So using properties of exponents again, we can say that this guy is 2 times 2 to the negative 2 power. I know a lot of 2's here. A negative exponent would be taking this base and moving him to the denominator, and then that would change the exponent to a positive. So 2 to the negative 2 would be the same as 1 over 2 squared, which is 1/4. So this is 1/4 times 2 to the x. This is the same thing here, right? So you can see that a shift to the right would essentially create an a value that's less than 1, where a shift to the left would essentially create a new a value that's bigger than 1. Okay? But I don't want to take this approach. I want to consider again that if a is 1, then we can kind of force a to be 1 by just moving our function left or right and creating this transformation, right, by just shifting it left or right instead of considering a new a that could possibly also make these, right? Okay, so let's give one a try. I think we're ready. We have all the information we need here. Okay. All right, so we got this graph, right? We know that the basic form of an exponential is going to be a times b to the x, but it could also have horizontal shifting, or it could have vertical shifting, right? Now, remember, if a is negative, it would be a reflection over the x-axis, right, just in case we see this. Now, we know that a basic exponential function has a horizontal asymptote starting at 0. So when we're looking at this graph, or any of these exponential functions, we're going to actually start off with the k value, because if the initial horizontal asymptote, right, for a basic exponential starts at 0, then it becomes very obvious to see a vertical shift, because if it's shifted up or down, then that asymptote would shift with it. So for this case, we can see that it's going to kind of flatline here at 1, so that means we know we have a horizontal asymptote here at 1, right? It would go on forever, right? Which means that the k value should be 1, because we would start at the origin and then shift it up, right? The whole graph shifts with this asymptote. Okay. Now, to figure out any horizontal shifting, we're going to consider that we're going to let a be 1 each case. So what we're looking for, right, is we're going to go to our asymptote, and we're going to look for the value that is 1 unit above this asymptote. So I'm just going to start over here, right? As we move along, we're going to wait until we hit the function at 1, which is here, which means the new origin, if we shift it horizontally and vertically, would be 1 unit up below this initial point. So here would be our new origin. So that's going to give us our shifted value left or right, our shifted value up or down. We knew that it was going up because we can see pretty obviously where the asymptote is, the horizontal asymptote here. But now we can see that it's shifted to the right 4, which means whatever b is, right, which I haven't determined, is going to be raised to the x minus 4, right, because the way we shift looks backwards from the way we write it. Okay, I'm forcing a to be 1 because I made sure that it was 1 unit above this. Now I'm going back to my main points. If I go to the right 1 from here, it should be a times b, which is 1 times something. So if I move to the right, I come up here and I can figure out where my function value is, which is 3 units above. This value should represent a times b, But if a is 1, 1 times what is 3? 3. So I know b has to be 3. Right? If I wanted to double check, if I come to the left, it should be a, which is 1, times the reciprocal of 3, which is 1 over 3. This does look like it's 1/3 of the way here. So this is looking pretty good. Right? So I don't really need the 1. I don't really need the parentheses. So I'm just going to kind of clean this up a little bit. It would just be 3x minus 4 plus 1. Right? There's our function that's graphed. Okay. All right, let's try another one. So same idea. The most obvious piece of information that I can pull from this guy would be the asymptote. So I'm going to start there. I can see it comes down in flat lines right about here. Right? Technically, it doesn't touch the asymptote, even though it kind of looks like it visually. Right? Again, I want to look for where it's 1 unit away from this asymptote. So as I move along, I can see that it's 1 unit away right here, which means my new origin gets placed 1 unit below that. So I know I'm forcing a to be 1, right? That way I don't have to think about some a value that could be anything. Okay? I haven't figured out what b is yet. Here is our original origin, right? So if I shift it down to here, that'll be left 3, so that's going to be x plus 3, and then I went down 2, right? Now I just need to figure out what b is. Now, if I go to the right, it should be a times b. It is getting smaller, so sometimes it's hard to see if that's going to be I mean, it kind of looks like a half, but maybe we're not really sure. So in this case, I'm going to go 1 to the left. So if I go 1 to the left, it's 2 units above it. Remember, this is 2 over 1, if we want to think of it as a fraction. But moving to the left, that means that this guy is the reciprocal of b. So the reciprocal of 2 over 1 would be 1 over 2. And the shape of it supports this, right? Because an exponential function going down to the right has a base value that's less than 1. If the function is going up to the right, it has a base value that's bigger than 1. So both of these kind of meet that criteria. So 1/2, right? We can see that it is 1/2. We knew that if we went out here, 1 times a half is a half, so that does look like a half. Okay, I don't really need the 1. I do need the parentheses to make sure that this whole thing is an exponent to the fraction. So I'm going to leave that, and I can just say x plus 3 minus 2. There we go. All right, let's try one more. So, same idea. I can see that it's got that kind of exponential shape to it, right? So that means that I'm going to start with the asymptote. Now, whether it's facing up or down, we can still see that it's approaching this asymptote right here. Right? Again, I want to know where the function is 1 unit from the asymptote. So since it's below, I'm going to look to see where it's 1 unit below. So as I scan the graph, I can see it's 1 unit below here. Right? So I'm ready to make my exponential function with its shifting, right? Because this is my new origin. So that means, again, I'm letting a be 1. I haven't determined what b is. I know that since this is my new origin, I got shifted left 1. So backwards from left would be plus, right? Because these are negatives. And I shifted up 3, so it's just going to be a plus 3. Right? I'm going to go to the side that gets bigger. Would be an easy way to do it. If I come over here, it's hard to see what that is. But over here, it becomes a little bit more obvious because the numbers are bigger. So from here, 1, 2, 3, it looks like it's crossing here at 4. Right? Now, when it gets to the right, we know it's a times b. Right? So b has to be 4 for a times b to be negative 4. But what makes it negative is that a could be a negative 1. right? Because the base of an exponential can't be negative, but the a value, the initial value, can be. So it is a distance of 4, so that means my base is 4. But since I went down, I'll put that negative on the a value. Okay. So I don't necessarily need the 1. I don't necessarily need the parentheses, right? So I'm just going to say negative 4 x plus 1 plus 3. Because remember, order of operations, I would do exponents before multiplication. So I can leave this negative without parentheses, right? Because I would do the exponents first. Again, if you're not sure and you want to try it out, negative 1 times 4 is negative 4. Over here, it would be negative 1 times the reciprocal is 1/4. I mean, it does kind of look, I mean, this is a half, so it does look like it's about 1/4. So it's looking pretty good. So there you go.